So in this video, I want to focus on naming molecular compounds. And it's really the last class of molecules that we need to memorize a whole set of rules, etc. And they're not too bad. We actually borrow a little bit from the ionic nomenclature, to tell you the truth. Like, for example, sodium chloride here. What we did was, the first element, we just use the element's name. And then the second element, we use this IDE ending. We basically use that same format for molecular compounds. So that's one thing to note. Now, the molecular compound that we're looking at here is, we know it as water, but we can also name it in a proper way. The name is never used, but you can do it. And let me just share that with you. So this can be called dihydrogen monoxide. If you Google this topic, you'll actually find plenty of websites telling you how dangerous dihydrogen monoxide is. Right? You can drown. Right? Again, we always call it water, but using the name, the rules that I'm about to lay out, you can call it dihydrogen monoxide. Notice the similarities between it and the ionic substances. Well, first thing, it's just the element's name. That's the first name we use. And then on the tail end, right, we use this IDE portion. The new part are these Greek prefixes that tell us how many of each of the elements we have. Di, mono. For 2, for 1. Which, right, 2 to 1, that's just the 2 and the 1 in the formula. And that's about it. There's a few other rules. Let's illustrate that with a couple examples here. And also illustrate why we actually use these Greek prefixes for the molecular compounds. Okay, nitrogen oxides. There are at least 4 different ways for nitrogen and oxygen to come together. It can be at a 1-to-1 ratio, 2-to-1 ratio, 1-to-2 ratio, 2-to-4 ratio, and there's probably others. Who knows? So we can't just simply say nitrogen oxide. That doesn't cover our bases. We have to introduce these Greek prefixes so we can deal with the 2 and the 4 and the 2 and the 1, etc. We did not need the Greek prefixes here because sodium was always +1 charge, chloride was always a -1 charge. They always come together in a 1-to-1 ratio. We don't need mono in that name. It's redundant, honestly. We have to have the Greek prefixes here to get the exact ratio right. So let's name these. And along the way, I'll share a few little rules with you. So this one is called nitrogen monoxide. This one is called dinitrogen monoxide. This one is nitrogen dioxide. And now this one is dinitrogen tetroxide. So what are some of the patterns? Well, one pattern, just a repeat of what I was saying a minute ago. First element, element's name. Second element, we use that IDE name for it. We are using Greek prefixes, but notice there's a few little subtle issues here. For example, we don't use mono when it's on the first element. And there's no mono there either. If there's 2 or more, then we use the Greek prefix at the beginning. The other thing to notice, and this really only deals with the oxide name, notice I did not say monooxide or tetraoxide. And so what we see in here, O is dropped on mono, and then here, the A is dropped. So what's in red here are some of the subtle issues you have to keep track of when you're naming these molecular compounds. Now, that A being dropped, notice that would apply to all of these. So if you had something, there's a P2O5 compound or O10, I can't remember. Doesn't matter. I can still name it. Diphosphorus, not pentaoxide, but pentoxide. So again, right, that A is dropped. And that's it. Based on these rules in this short lesson, you can name any kind of molecular compound that you'll come across for this chapter. There's a whole category of molecular compounds that you would deal with in organic chemistry. There's a different nomenclature set of rules for that, okay? Now this video is short enough. I just want to go ahead and add the nomenclature for acids as well. And instead of getting into some long drawn out set of rules, we're just going to memorize a short set, this set. It includes really the most common acids that you come across in general chemistry class. You may have already seen some of these in some of the labs. Carbonic acid, it's an important buffer in the blood, or part of the buffer system in the bloodstream. Briefly, what's happening with these acid names is, like, notice that the formula here, this is that acetate ion that we saw in the previous video, carbonate. And look what's happening. 8 ending here. What's the charge? It's a -1, it's a -2. Notice there's 1 hydrogen, 2 hydrogens being placed there. These hydrogens are actually protons. They have these positive charges. Chapter 14, we'll learn about acids and bases a little bit in this class. But basically what you're doing is, if there's a -1 charge, you add 1 proton. If it's a -2 charge, you add 2 protons. And when you do that and you form this molecule that does not have a charge, that's where the acid name comes from. And then finally, notice instead of an ATE ending, we use an IC ending. So similar to what we saw in a few cases previously, there's a conjugation, there's a change in the prefix to indicate that you went from one type of compound to another type of compound. You don't have to memorize all those rules, just a little context about what you're looking at. You basically just need to know these names. There's one more topic for this chapter. Let's just go and take care of it. Our textbooks are referring to this as the formula mass. Sometimes it's also called the molecular mass or the molecular weight. Basically all it is, and there's an example here for this, carbon tetrachloride. By the way, this is a molecular compound. We got carbon, chloride, both are nonmetals. There's 1 carbon, so mono is not used in front. There's 4 chloride, so tetra is used. Remember when I said the O and the A are dropped here, that's just for oxide. We want to determine the molecular weight for this compound, or again, formula mass. And all you're doing is you got to interpret the formula correctly. So there's 1 carbon, there's 4 chlorines, and then you go to the periodic table. Each carbon weighs 12.01. This is the average atomic mass. Each chlorine weighs 35.45 AMU. Let's see where these numbers are coming from. There's carbon, there's chlorine, and it's just these bottom numbers, that average atomic mass. And again, for a test, you'll have the periodic table, so you don't have to memorize all these numbers. Multiply each atomic mass by however many atoms are there, and then you sum everything up. So that's the formula mass or the molecular weight for carbon tetrachloride. Let's do this example with the dinitrogen monoxide, nitrogen oxide compounds that we saw a few minutes ago. I've pulled the information from the periodic table. There are 2 nitrogens. Each are weighing 14.01 AMU. There's 1 oxygen. It weighs 16.00 AMU. So notice what I'm doing here, and this is fairly typical. We're going down to the 2 decimal places and then rounding up where appropriate. That's where I'm getting the 0, 1, 0, 0. Usually if you go to 2 decimal places, then you will have enough significant figures so that your calculation, the answer from your calculation matches up with an answer from the multiple choice test or some problem on Mastering Chemistry. If you leave out some of the digits here, occasionally it can be a little confusing about which is the correct answer. Anyway, recommendation, preference, go to 2 decimal places for all of these masses here. So 14.01 times 2, well, that's 28.02 plus the 16, 44.02 AMU. And for this chapter, that's as much as we're going to do with this data. In the next chapter, we'll actually use this information to start doing calculations with chemistry. That's our chapter 5. Thanks.